Hello, class. This is the 1/2 lecture. You've probably already seen lecture 0, and this would be lecture 1/2. And I can never get that right. Anyway, I wanted to go over the lecture syllabus with the class. And so if you could all take out your lecture syllabus and look at that for just a second. I just want to go down through that and just sort of touch on a few things. Introduction, that's lecture 0. Derivation of Maxwell's equation, that's really lecture 1. And that's already been done. That's an interesting lecture. I'm sure that you'll enjoy that, even though you may not understand all of the mathematics that are going on in the derivations that I'm going through. But it's enjoyable because it sort of jumps to the end point of what Maxwell's equations were all about. And then, dimensions and units, dimensional analysis, gravitational force as an analog to Coulomb's force. All of those lectures have already been done. I haven't done a lecture on electromagnetic spectrum, but I think that you guys will start to see that. And I'll be putting a lot of other important formula that you're going to see and you're going to be using later on in the course into these lectures on the first parts anyway. After electromagnetic spectrum, we're going to go and get into vector algebra, which is really a review, I think, for a lot of people who have had me for engineering mechanics, but we're going to take that just to the point where you understand dot products, cross products. So it's, like I say, a review. Coordinate systems, and these are, of course, all out of Fawaz Alabi too. I want to point out that at the end of the topics in the lecture syllabus, you'll see that there's some numbers like 1-3 or 4-2 or whatever it is after the end of some of the topics, and those correspond to the reading sections in the Electromagnetics for Engineers textbook that we're using. So anyway, going past that, coordinate systems and transformations between coordinate systems so that we could sort of understand really what the 3 different coordinate systems are. That's one of the things that you really want to learn and take away from this course. It's in many curricula, it's the only time that you really start to look at the differential operators and look at those things in a coordinate system that's other than a rectangular Cartesian coordinate system. Really, if you think about it, if you think about the way that a wave moves out from an antenna, let's say an omnidirectional antenna, and the wave, here, I'll put my hands up, the wave, oh, where? Here. The wave's moving out from the antenna in a spherical, right? In a spherical manner. And so Cartesian coordinates don't lend themselves to a spherically emanating waveform, but spherical coordinates do. And so we have to know how to do transformations between spherical coordinates, Cartesian coordinates, and then cylindrical coordinates too, because there's other things like coaxial cables where the wave is traveling along a cylindrical conduit, wave conduit, inside the foam, basically. That's where the wave is traveling. We'll get to that later when we get into transmission, chapter 8, transmission lines analysis. So anyway, let's go on from there. After we get into that, we start to get into the del operator and looking at gradients and divergence, curl of a vector field. We'll talk about that. That, of course, has a lot to do with the first lecture that or lecture 1 that you're going to have on Maxwell's equations. And so we're going to probably use some of that time to not only look at the mathematical properties of the curl and the gradient and all of that, but we're also going to try to understand what's going on with that and how it's going to be used in Maxwell's equations. Really, what is Maxwell saying with his equations? They're not that hard to understand in differential or integral form. If if you think about it. So we'll talk about it, right? You want to understand what's going on inside those equations. And then we'll get into charge, atomic structure, and elementary particles. Of course, elementary particles have charge. Protons have a positive charge. Electrons have a negative charge. Neutrons have no charge. What if we have various different particles that are charged particles? They then develop an electric field around them. So if I have a charged particle that's a positive charged particle, it's going to have that positive electric field around it. If it's a negative charged particle, it'll have a field in the opposite direction around it. And those are going to interfere. Those electric fields will interfere with one another. But we can use superposition, looking at the effect of one of those charges at a point in space, and then looking at the effect of another charge at that point in space, and then vectorially adding those forces together, right? And then we'll look at the voltage too, how the voltage would change across that electric field. And we'll start out with looking at, very common planar electric fields, and then we'll expand to higher geometries of those types of electric fields and multiple point charges rather than just one charge or two charges. See what I mean? Then we'll get into Gauss's law, which is really just, that's just a derivation. I'll talk about some of the applications of that. Anyway, electric potential within an electric field, that's really the voltage field that we're looking at. The voltages all through electric fields, and electric field with multiple point charges. And then we'll get into magnetostatics. And I have an idea that you guys have taken a motors and controls course. I think that was in our curriculum. So if you've taken that, then you've probably been introduced already to a lot of what's in magnetostatics, Biot-Savart law, just really what is in magnetism. And I'm going to go into a discussion on magnetism, because there's a deeper understanding. Try to give you guys a deeper understanding. So you're going to get coordinate systems. You're going to understand what the del operator is. You're going to understand what divergence and curls and vector fields and scalar fields are. You're going to learn how to use Coulomb's law in the correct way. Yes, that's right. If you remember Coulomb's law as, let me just write it down here. Here, I'm going to show you the other camera. The other camera. How about that? That's right. That's my other camera. So let's just look at a couple of these things. Now, what did I want to write down there? Amperes law, no. Biot-Savart law, magnetostatics. We sort of got into that. No, I can't remember. Maybe I just wanted to show you my pad of paper anyway, and that's what we're going to be working with anyway. I'll remember. I'll go back and I'll look at this and say, oh my God, that's what I was supposed to teach them. Anyway, let's go on. Amperes law, that really comes to the end of, and then Maxwell's contribution to Amperes law. Those are really what you're going to see in lecture 1, 2 for the first time. But then we're going to talk much more about them and really what they mean in Maxwell's contribution to Amperes law and things like that. Transmission lines, that's a large part of this course, is really understanding how waves travel down transmission lines, right? That's it's electromagnetic waves. They're traveling down that coaxial cable. They're traveling down those high tension power lines. They're how are they doing that? Are they traveling on the wire? Are they traveling on the inside of the wire? Are they traveling on the outside? I mean, how is the voltage that goes from the power generating plant out to your house and goes on those high tension, power lines that you see as you drive along the highway? Where is the voltage being transmitted? Is it on the outside of the wire? Is it on the inside of the wire? Is it in the air? Where is it? And of course, it's traveling down the wires. It's traveling down the space between the wires. Just like when you think of a coaxial cable, you think, oh, well, it's the signal wire in the middle. That's where it's traveling. No, it's not traveling there. The wave is traveling through the dielectric foam inside, right? Because it's a voltage wave between the signal wire and the outside ground shield. You're going to have that ground shield. So, and of course, this is interesting too, isn't it? Let me just point this out. Now, if I've got a coaxial cable and I've got the center wire, right? The center wire is positive. Let's say it's positive 1,000 volts. And the outside ground shield of that coaxial cable is 0 volts. Then isn't there a voltage difference between those two? Isn't this a conductor and this a conductor? And isn't the foam in between the signal wire and the outside ground shield a dielectric? Oh my God, we've got two conductor plates at different voltages with a dielectric in between them. What is that? It's a capacitor, isn't it? So I'm sure that you're thinking, well, there has to then be some type of capacitive loading on that coaxial cable as that, signal goes through that coaxial cable. And you're probably thinking to yourself, God, I wonder if that's frequency related. I wonder if it's a higher frequency, I would have more capacitance, or if I had a lower frequency, if I would have more capacitance on that line. A lot of things to think about. And so that's what we're going to think about, and we're going to look at, and we're going to see what the propagation things are. You're probably thinking, well, it has resistance too. I mean, it's made of copper, so it's got resistivity. It's not a superconductor. You can't run something from Boston to New York on a coaxial cable that you've got hitched up in your garage, can you? Or can you? And so those are all questions that we want to look at and ask. And what we really want to find out at the end is, if you look down here, you're going to see that we start later on talking about the attenuation constant and the phase shift constant, right? And that's what we're going to look at. We're going to look at where is the energy going and how is that affecting the signal as it travels down that transmission line, whether it's a power line or whether it's a coaxial, radio frequency line. And then after we get done with that, we're going to look at voltage and reflection coefficients, standing waves. We'll probably end up with looking at a Smith chart, and I'll teach you how to use a Smith chart so that if you ever get out there on a job and somebody says to you, have you ever used a Smith chart? You'll say, oh, sure, yeah. Professor Grenquist taught me how to use a Smith chart. Is this for parallel stub matching? And he'll go, why, as a matter of fact, it is, because that's all we do. We only do parallel stub matching. We don't do series stub matching here. I don't know what he's going to say. But you'll know how to look at a Smith chart and use a Smith chart and why a Smith chart was put together the way that it was. It's all complex numbers. Everything we're doing is complex numbers. Everything we're doing is differential calculus. It's so much fun. I'm sure you're just looking forward to all that. The very last one here, after we get done with the fiber optics, because I'm going to put together like 4 or 5, 6 lectures on fiber optics too, so you can go as deep into that as you want. I may even think about doing. I used to teach fiber optics, so I may even do the whole course and then just set that off to the side or something. If for some reason I enjoy doing this. All right. And then the very last one, I just want to look at microwave tower height and transmission distance analysis, because the microwave transmission is line of sight, like FM. And so as high as you have the tower, and you probably realize there's a lot of microwave towers, a lot of high towers with microwave, horns on them transmitting. And, how far can you go then? And that has to do with the curvature of the Earth and the height of the tower, and also the decibel attenuation of the signal. What is the decibel attenuation of the signal? Because in actuality, you could probably go to like, minus 90, minus 120 decibels if you could get a tower high enough. But then, is that easy to pick up on the other side without any type of error? So those are questions that you want to ask too. Okay, well, that was lecture 0.5, and then I want you to start on lecture 1, and I'm going to keep putting lectures up there. I will try to set up a Zoom meeting for what I think is Friday morning. I think both of these classes are Wednesday, Friday, so I'll try to set up a Zoom meeting with the email addresses that I have for Friday morning, and you can look at the other lectures at your leisure, and I will be sending out homework and stuff too, in addition to more and more and more lectures. All right. Stay safe.